Hey everyone, welcome back to the channel. My name is Matt Dickinson, and in the past 7 weeks we've been doing a lot on the Hardyman project. This week we're doing a little bit different. The project is still very much a go, so please don't think that that is the end of it. But we're going to do a bit of a short tutorial on using Ansys for topological optimization. So let's not mess around, let's go straight back down to it. Let me shrink it right down to here. Make that a little bit bigger. Okay, so you guys will not have seen this as of yet. This is an exoskeleton which has been designed to enable kids to actually really understand what exoskeletons are for, help with education. This originally started out as one arm, and I received feedback that it was too complicated, so it went from something like 15 parts down to 4. So it's 1, 2, well, it's actually 1, 2 there, 3 and 4 attached on there. And I've recently added a shoulder blade on each side so that we can have a microcontroller. Really, it's interesting. We've gone through this so many times that this exoskeleton now is actually becoming a bit more of a viable exoskeleton. So just for you guys, it uses Picatinny rails. Thank you, Aiden, if you are watching. Great idea. So one of the student chapters suggested Picatinny rails for quick release and access. And it uses Picatinny rails for the shoulder pieces as well, but the problem is it kept falling off your arm. Right, so let's not mess around too much. You'll see here that the arm itself was originally designed to activate around the elbow. Now this section here is the brace piece. So what I've gone and done is I've gone ahead and I've taken a base material chunk. This is from the original design, and what we're going to do is pass this into Ansys and let this run through. Now the only reason I've not given you this is just because we still need to, this has now been physically tested, and as to date, which is the 4th of the 11th 23, we've not tested it yet, but coming this Wednesday we should be doing that. So if you are interested in having a go and building your own, let me know. I will free you up and you can get your own designs for free and build your own. It is a lot of fun if you've never seen this thing before. Anyway, so let's not digress too much. So this is going to be my piece. Now what I want to do is I want to use a system in Ansys called topological optimization. The idea is when stress occurs, in fact, let's not mess around, let's get this out, then we can manually see this. So the reason I've gone to my inventor is because most people nowadays tend to use a CAD system outside. So I'm going to export. For this example, I'm going to put it on my desktop. Oh no, I don't want a shortcut. I'm going to put it on my desktop, and I'll just leave it as a new file. But what I want to do is I'm going to export it as a step file. I personally always operate in step files, and I'm going to click OK. Now in Ansys, now this is Ansys release 22, and in Ansys, what we have here is our overall interface across, and I'm going to drag and drop a static structural approach. What I'm going to do first is I'm going to look at the arm piece when somebody is holding a 20 kilo weight. We'll calculate out the force, because obviously it's 20 multiplied by 9.81, and that will give us the force that's applying around the key points of what we're going to attach to. But first things first, let's bring in that geometry. So I'm going to right click, go to import geometry, and browse to the position where my geometry sits. Right click, and I will always recommend that you review this. So I'm going to use Space Claim to review the geometry. You can use Space Claim as a CAD system, but I only ever really use it to review the geometric representation. After the part is imported, you'll get it brought in, and it's similar to any CAD system, if anybody's used to it. So as ever, you can spin it around, have a good look around. On the left side, you've got your design tree. Structure sits here. I can disable the solid and have nothing, or I can re-enable to ensure Very, very basic principle process, good for reviewing and changing when needed. Okay, so I'm happy with the component. So I'm taking that back out. For this particular one, I'm actually wanting to see how well this will perform. Not a structural steel, but I'm actually going to do it as an aluminium alloy. So, let me just go to aluminium alloy. I'm going to go to my general materials, bring that up, and scroll to a position, and I'm going to add the aluminium alloy. So aluminium alloy is in my study. Close this, and then I'm going to go to my setup and then right click and then edit. And after a couple of minutes, depending on your PC and your on the PC's capabilities that you're operating with, you will then get your geometry in. Now again, I'm just taking this purely from my Exo design. Once we've tested this and I'm happy with this, I'll release these designs anyway, so people can have a go. For my material, I'm going to go to my geometry, and if you remember, I assigned aluminium alloy, but it's still structural steel, so I'm going to drop my assign, and I'm going to change it to an aluminium alloy. Now what I'm going to do is fix to a normal meshing procedure. I'm going to just do a couple of things on this. I want this to be as, if you look round, as that as a whoops. If you look round as that as a piece, it is quite chunky. I'm not quite happy with that. But first things first, let's just get a little bit of things going on. I'm going to presume that it's like fixed on this face, because based on the original geometry, that's how it actually fixes. It fixes around here when there is a plate that interfaces with the elbow. So we're assuming that piece here to be fixed. So what I'm going to do is come back to my static structural. I'm going to insert, and I'm going to go fixed. So I'm going to come to here, and then I'm going to apply. So that now applies to that position. Now, the way that this works is we've got parts all the way down here, and it's supported at key spots all the way down. What I'm going to do is I'm going to assume that it's just held on the end piece, because I don't want this tutorial to go on forever. I just want you guys to get a good idea of how to actually interface with this topological optimization feature, which is a fab feature if you do get a chance to use it. So I'm going to go force, and I'm going to come across here. Now, in my force, I'm going to go this piece and this piece. These are the two holes that mount the Picatinny rail for the wrist. So I'm going to click apply. And at this point now, I'm either going to go vector, where I can choose which way I want to go, or I'm a bit of a stippler. I like to use component. So in this case, I'm going to go, right, so how many newtons do we need? We need, so we're going to presume, let's go 30 kilos. I think we're saying 30 kilos. Let's go 30 kilos. Multiply by 9.81 for acceleration, giving us 294.3 newtons. But if I go over 2, because it's 2 divided over area, so let's divide that by 2, and it gives us 147.15 on each key component spot. So I'm going to go minus 147.15 and then go apply. You'll notice I'm in the Y component, telling me I'm going downwards. Okay, so now what I would need to know is I'd like to see how much it's displaced by. So I'm going to come to my solution, I'm going to right click, go insert, I'm going to go how much have you displaced by, so how much did you bend in that process. I'm also going to go insert and stress for equivalent von Mises, and then solve. This then runs through the solution, as we all well know, and any minute now it should give us a result. So the solution, and if I just take a look around, it's quite chunky, quite a little bit unreliable. So I'm going to go to my edges, just going to turn that off for a second. Look at that. Oh, it's horrid, it's awful. However, all this section here, one important thing here is this section here is this red and this red, this area. Well, then you look down here and there's all this blue, and look at that, there's next to no stress going on there. This leaves a huge optimal opportunity to do topological optimization. First things first, I'm just going to quickly make a quick mesh to just tidy this up because I don't like it. So I'm going to go sizing, and I'm going to come, let me just bring you out a little bit. I'm going to go U, oh, apologies. I'm going to go this area, I'm going to go this area, and I'm going to go this area, and I'm going to go here, and here, like that. Apply them into there. And size-wise, look there, default 12 millimeters. Boom, that's massive. So I'm going to go 2 millimeters. And then let's just resize that. 3, 2, 1. It's still a bit chunky there. I'm going to go 1 millimeter. Give me something a little bit more. Come on. So again, generate that again. Looking a little bit more like it. Yeah, okay. I'll probably drop it even further. I want to get some true representation of what's going on right now, and that's a little bit better. Now you see there how that means that if I just run this, just solve this again, it may allow for a little bit better of an optimizational process what I'm after. So it's not perfect, but it's a lot better. Interesting, let's check it out. It's not the highest spot. I thought that would be the case, and look at that. It's actually where I'd imagine, concentrating on the edging, which is good. And also down here, look at that. Oh, look at that. Now that's purely because if you have a quick look, squeeze, squeeze. That's all that is. It's just squeezing on that lower spot. So what we're going to do then is, it's fine. You know, it's well within the remit of what I want to do. So now I'm happy. I'm going to come out of there, close that, and now this is cool. So I'm going to go down to structural optimization. I'm going to drop it over solution, and watch this. Bang! Results shared. Everything's within it. Right click. Let's go in and edit. Okay, so now once we've double clicked into topological optimization, you can see here that the design region topological area for a review, Ansys is already noted on here where it's actually going to be used. So you can see here where you got your region of A noted here to be the design region for topological optimization. You've got regions to be excluded, which it automatically excludes the boundary conditional areas. And then you've got correspondence for container of 50% of mass, and nothing is on there as of yet as what we've actually got to do. So if I come down to my analysis, we're going to leave it at 500 iterations and trying to converge at an accuracy of 0.1. What we're going to do from there is for output controls, we can choose different types of files for outputs. I mean, we'll come back to this in just a moment. But let's have a look. So optimization regions. So within my optimization regions, what we can make some changes. We can look at all bodies, or we can look at alternate conditions for boundaries. We can look at all different types, but we're actually going to leave that. So this is where it's quite cool. So we're going to go objective. So under the objective, this is the default. So we're going to program controlled under static structural results, and it will run all compliance from there. And then we have response constraints. And I know for sure I've missed something out here, but I'll come back to this. I think the output controls, I needed an output control, but yeah, if we come back to the constraints, you can see on here. What I'm going to do here is I'm probably going to change my percentage material to retain. I mean, I'll go 65%. We can drop that down, but what this will do is it will run through topological optimization as many times as possible to try and get the most optimal thing on here as it runs through. So once I come back, I just wanted to check on something. So output controls, output design. So let's have a look. File to region, it's not that. What's it to iterations? No, it's not that. Look. Drive me mad. Ah, right, hang on. So under my here we go. I was looking on the wrong spot. So for post processing, you see there it's only geometry. I can go only geometry yes or only geometry no. Topological density. I can actually go where is my STL export? 1 second. So now, based on everything that we've got on here, based on the topological, what we're going to get, we should be now ready to solve. So if I now hit run, if I solve, once it's done, you'll notice here I've just clicked onto topological density tracker, and this now shows the processes that it's going through and how many iterations it's going through and the changes it's making. We can instantly see there that the 65% material loss that I've suggested is not the best option. I mean, it's given us different types of solutions here, so let's just run it through what it suggests. Yes, so you see there that it's the 65% is way too. I should have really planned this one. So I've gone to change my percentage material retain, and rather than going for 60, I've gone for 85. Might even go 90%, just to give it a little bit more of a possibility of survival. So what I'll do here is come on, and I'm going to click on my topological density tracker and then hit. And if I try this again, had a couple of moments there where it just went on and off. What I'm going to do is I've now changed it to 85%. I'm on topological density tracker, and then let's go solve. Boosted it up. The regions were just too much. And really what I could do is actually restrict even further areas, which I think I'd like to be able to go back to. So let me just go. What I'd like to do is to restrict key particular areas, and in this case, I want to make sure that where the Picatinis are mounted, that they are also taken into consideration as well. So basically, where the holes sit, I think I'd like to just restrict them areas from that particular study as well, to make sure that it's going to give me something sensible with that. And any minute now, we should start to get a solution. And here we go. Let me go solve. Yeah, this is just because I'm rushing through my typical sim. But you'll see there, it's optimizing right down. It's chopped as much out as possible. It's got 80% retain of 80% material. But you'll see there, it crashes like mad because it's going. That's what it's actually done. And that's what it recommends, and you go, no, that is not what I'm after. So if you just see there, it just chops it all right back. And then what I'll do is I'll say, right, so let's optimize the region. Let's retain 20%. And then I'm going to do it again. So I'm going to solve. If it's not going to have a dippy fit with me, because now I'm going backwards, I'm going all over the place. So we'll let this run through. So I'm now at 20%. So you're probably wondering, why is it doing all this weird stuff? Why is it actually creating these really odd regions? These normal regions actually appear just because the optimization regional areas here, let me just rerun that, optimization regions here that run, these actually appear purely because this design region for topological optimization, you basically said use anywhere on here, and it doesn't know to keep it all in play. And those of you who've seen generative design functions because what it does is it can optimize areas, and you can actually put in key regions to it. So what I'm going to do here is I'm going to say give an exclusion region. So my regions now, I know that I need these holes. I need these holes to be able to move forwards, and that one as well. These holes are there for actually where the other Picatinny rails are going to be. So I'm going to assign them. Next thing I'd like to do is offer another excluded region. So I'm going to go around the actual outside piece. What I'm actually referring to here is not really. I'm just colouring in, sorry. What I'm actually referring to here is not really on the outside face. I want these outside faces to retain here for this particular reason, because I want to be able to use the external to ensure that the assembly still works. What I want Ansys to do is to consider the insides. Is there something that could be done with them insides? So I'm going to just shift myself back. I'm going to say retain. I'm going to go back to 85%. This has just been me playing around. And what I'll do is I'll run to a solve. Now you'll notice that my my meshing's dropped a little bit. And I think I've lost one of my faces as I was just messing around. But what you'll see now is it starts to cut key particular areas out. And you look and go, okay, so that's based on the results that it's actually producing up here, these results, it's recommending that the topological design could actually do away with these areas and still perform based on what the criteria is. The only thing that I'm a little bit skeptic now is again, it seems to have lost my regions of refinement. So there, and as we well know, there. And I'm just going to add them back in because for some reason, as I said, I've lost them. So I'll go on there like that. And I'm just going to rerun this study once again. And if I run it again, what we start to see is it will run through that topological optimizing. And it's, again, the red regions are where I've said, don't change these, keep these in play. And if I go to my tracker, give it a moment. Now what we get is it starts to rerun its key particular studies areas. Now look at that. It's actually, based on that refinement that I've put in there, it's now starting to say, you know what, I probably can't do that. And you'll notice on the mesh here, it's quite clunky. I mean, arguably, the end piece, it's actually saying, you know what, you could actually perhaps trim that right back. If I want now, I can go to this and I can go to, I can come here and I can export. I can export to an STL straight outright if I wish. This is quite interesting. So if I just now hit save, and I'm just going to drop out of here. And now what I'm going to do is go back to another static structural. And from my results, I'm now going to bring it into the geometry here. From this, now I'm going to go into my study and go edit. Okay, so that just was not playing ball, so I've just removed that. And I'm just going to pass back into my original. Right, get back to this original. There we go. On for the topological density. You can see there what's been exported. So I'm going to export this. And I'll export this as an STL file. And let's just put this on my desktop. Let's go File. Stick it there. And then what I'll do is I'm going to take this through to my Cura. When it actually loads. So now what this has done is it's topological optimized the actual profile. And granted, I could run this through quite a few iterations yet to actually look at different changes that could be made. There is a bit, but this can now clearly indicate and help guide me into what I need to do on my next steps. This is quite a useful tool, and you can do all types of different things from here. So the equivalent von Misers for the strain. So let me just evaluate the results on there. And oh yeah, it's only just because it's something else. And what I can do with this is I can do all sorts to just look at the next iterations of this, and just to show you, if I'm in my Ultimaker, my Cura, I can come onto my file and then I can import the actual topological optimized profile, bring this right across to here, and if I just flip you around a little bit, you can see there I can actually produce the part based on what Ansys did. Now you see there that my mesh is quite big, but it is a good insight and a good indicator to getting it running. Right, so I hope that you all found that quite useful. I hope that that's been a good insight. This has been topological optimization, and using this for exo designs, in particular the exo, we've actually not named this project. I didn't think it was going to become something that would need naming, but this has been purely based on the exo that's going to be the one for public engagement, and it has now become a shoulder exo. If you are interested in that, do get in touch, drop me a line, and I will try and get back to you as quickly as possible about that. Our physical testing, our very first people who are testing this will be the ASDM student chapter this coming week. Other than that, have a great day, everybody, and I will speak to you in a week. Thanks, guys.